so that we can review the math on Thursday, so that I don't just cover it on Thursday, kind of like the only time. So we're going to kind of mix up the theory and the math just a little bit. So first thing, we're talking about solutions and what solutions are. Remember that there's those true solutions, and those are where the solid molecules are very small. They mix, they stay mixed. But then you can also have colloids in suspension. So those are other types of mixtures, right? So remember, mixtures are things that are just physically combined. Colloids are when you have large molecules, they don't dissolve. Well, they don't separate. They do dissolve, but they don't completely separate. So a colloid, and I think we talked about them back here. The colloid, large solute particles that mix into the solvent, they don't separate, but they make that solution kind of thick. Cream, jello, gravy, egg whites, all examples. And it's really because the solutes that are dissolved are really large. So cream, you put cream in your coffee, it completely mixes, but that cream doesn't separate itself, stays mixed. But a suspension, I told you, is when you have solute particles that are not dissolved, but you disperse them by shaking or mixing or having that solution move. Once you stop, then it's going to settle. So I gave you the example of the dirty water, amoxicillin, a lot of medications like liquid medications. If you have to shake them, it's because they do not stay mixed. They separate with standing. So blood is kind of a mix of all three. So blood is a colloid because blood has large proteins. They are dissolved in plasma. And it actually makes plasma. Plasma is the fluid part of the blood. They don't separate out, but they make that plasma thick. But blood is also a suspension, and that is because blood cells, red blood cells, white blood cells, platelets, they are in the blood and they float, but if the blood stops moving, they would actually settle out, kind of like the amoxicillin medication. The only reason that blood cells stay as a suspension is the fact that the blood is constantly moving. So they are kept mixed due to the blood's constant circulation. And so down at the bottom, they show you can actually separate the suspension of blood either by letting blood sit, where the large particles, the large cells would start to settle out, or you can separate it by centrifugation. So if you were in lab, we did centrifugation as a way to separate the sugar components in a banana and the starch components in a banana. So by centrifuging, it's very much just like a big washing machine. So washing machines like spin around to pull the water out of your clothes. Well, this spins around everything that is more dense, settles to the bottom. And so you can see in this very dark red material that's in the bottom, that are the blood cells, okay? So this is your red blood cells, very dark color, very solid looking. But then all of this area that is kind of this yellow, clear liquid, that is plasma. That is the fluid portion of the blood. And I don't know what kind of person, animal, creature they took this sample from, but this person's like seriously anemic, okay? Because what component of your blood should those red blood cells be? Any idea? Not that little, because that looks like maybe it's 25%. So your packed red blood cells should be somewhere close to half, which is why I say that when you look at that tube. I'm not sure why they would put that in a textbook, because that is like very misleading. It makes it look like that's the norm. So you really should have about 45% red blood cells. After you centrifuge blood, anything below 35% is considered anemia in a human. I'm not sure with dogs and cats, but I can't imagine that it's going to be a whole lot less. Red blood cells carry oxygen, so that is why you need it. And about 55%, that is this plasma, the fluid component of the blood. White blood cells and platelets, they are actually less dense than red blood cells because they don't have iron. Red blood cells have iron in them, which makes them very dense. That's why they all settle down into the bottom. But, and you can kind of see, do you notice like in this one, it looks almost like there's this little layer on top of the red in the image. So in that right here, that little layer is actually your white blood cells and platelets. They're more dense than plasma, but they're not as dense as red blood cells. So they settle out right on top of the red blood cells. So your red blood cells and platelets, they call that the buffy coat, but that is typically less than 1% because they don't make up a whole lot of the blood cells found in blood. Most of the blood cells in blood are red blood cells. But that's kind of a normal. That's a way of showing that suspension, centrifuging, separates the components in the mixture. So when looking at this in the blood, we have red blood cells, white blood cells, platelets. Colloids, large molecules, but still the solution stays homogeneous. This is in plasma. So plasma has what are called plasma proteins. The plasma proteins that are in this, if we flip back, if you go back and look at that plasma content, that plasma yellowish looking straw kind of liquid, plasma proteins include albumin. Albumins are found in blood and they help to maintain water balance. Without albumins, you don't keep the normal amount of water, and so water ends up indiscriminately being sort of gained and lost. So albumins really help in water balance. You also have what are known as immunoglobulins. It's just a fancy name for proteins that are part of what? From the name. They're part of your what? Immune system. So think immune system, immunoglobulins. These are primarily antibodies. Antibodies are proteins that will stick to certain foreign substances, whether it's a virus-infected cell or a bacteria cell, or even an abnormal cancer cell. These antibodies can help to identify foreign substances and help to trigger an immune response. So if you've had chickenpox or you've had the chickenpox vaccine, then you have antibodies in your plasma that will bind to any cells that are carrying that chickenpox virus. So those cells, if they're infected by the virus, they will actually have proteins on their surface, and the antibodies actually recognize that. So remember in the last one we were talking about cell membranes and how those proteins have that identification, that cell identification function. So antibodies are constantly looking for that foreign substance that might be present in the blood. If you're going into nursing, and then one of the things you have to do is you have to give them your vaccination record. If you haven't had chickenpox, or even if you've had chickenpox, or if you've had the vaccine, one of the common things they want you to do is to get in a chickenpox titer. The titer actually measures the amount of antibodies that are present in your blood. And if it's not enough, then that means that you might get chickenpox. And then that means you might pass it on to your patients who have really weak immune systems. It could really be very hazardous for them. So oftentimes you'll have to get a booster. So you'll have to go get a chickenpox vaccine if you don't have enough titer or antibodies present in the blood. Third one, the last one, are clotting proteins. So albumin helps to hold water. Antibodies are part of your immune system. Clotting proteins are going to help to do what? They're going to help with clotting. Okay, so clotting is how you stop bleeding. So if you damage a blood cell, those platelets stick to if you damage a blood vessel, platelets stick to that torn, damaged blood vessel, which is why you're bleeding, because you've torn a blood vessel, so blood is coming out of that vessel. Clotting proteins help to kind of seal. They create a mesh to stop bleeding, and they're kind of like the final part in the clotting process. So they can help in forming a clot to help you stop bleeding. So those are all examples on how blood is actually a colloid, but then blood's also a true solution. So in plasma, what kinds of things are dissolved in plasma they're very small, they stay dissolved, they don't separate out. It's really the whole reason that blood moves constantly. What is it doing? It's circulating what? Oxygen. That's primarily carried by red blood cells, but what else is it circulating? Not only do you need oxygen, you need nutrients. Right? So glucose that's picked up in digestion needs to get transported to body cells. That's completely dissolved when they talk about your blood sugar. They're talking about the concentration of glucose in the blood, and that is glucose that's completely dissolved. So nutrients, vitamins, amino acids to build protein, the building blocks that you're going to need for DNA synthesis, all of those nutrients are part of or dissolved in plasma. They don't separate out. Salts, another example. So sodium levels, chloride levels, bicarbonate levels, potassium levels in the blood. So nutrients, salts, even wastes. So waste molecules made by your body cells need to get transported to the kidney, because it's the job of the kidney to filter out this fluid waste, to get rid of urea, uric acid, creatinine are the primary ones. So all of these are small molecules, totally dissolved, don't separate out. So they're considered a true solution. So the blood is actually a combination of all the different types of mixtures, all the different types of solutions that we've talked about. So if you have a solution, the solute content can oftentimes be variable. And so in here, we are sort of talking about coffee. So some people, they like their coffee with 1 sugars, right? 1 teaspoon of sugar, or 2, or 4, or 6. So maybe you like a lot of sugar in your coffee. Right? So that's variable. So the amount of sugar that you put in is variable. That, remember, is the solute. But now I could eventually take this sugar and add it and add it and add it. And eventually I would reach a point that I cannot dissolve any more sugar. At that point, they would say that that solution is saturated. Saturated means it has the maximum amount of solute it can possibly dissolve. And if you add any extra, it will remain as a solid in the solution. So here's an example. So this is whether you're adding sugar or adding salt. So this is sort of the coffee with 1 teaspoon, right? So the little white circles floating in. You could put more if it's not, if it doesn't have the maximum amount. They call it an unsaturated. So unsaturated solutions have less than the maximum solute amount. So I can add more, I can add more, I can add more, but eventually I'm going to get to the point that they can't have any more solute dissolved, and that is when it's saturated. And if you add any solute beyond, do you see the solid that is in the bottom? So you might remember this if you were in lab when we made soap. One of the things we had to do is add a saturated solution of sodium chloride at the very end And you remember that in those bottles, you had to put some in a beaker and get it cold. In those bottles, when you picked it up and looked at it, there was salt down in the bottom. So even if you like moved it back and forth, it stayed there the entire time. So I made saturated solutions of sodium chloride, and all that I did was take a sample of water and add salt and stir it, and add salt and stir it, and add salt and stir it until it didn't dissolve anymore. Okay? And that's a saturated solution. So there's some solid that remains behind. So there's an application for this. In the body, there are times when you may get to the point that the amount of solute is saturated, and any more will actually form a solid. So two good examples of this is what happens with gout and with kidney stones. So with gout, there is a molecule, and this is a waste molecule, that is made from protein synthesis, just cellular metabolism. It's called uric acid. And most people, uric acid is filtered out at your kidneys and it gets flushed with no issues. So most people never run into issues of having too much uric acid in the body because the kidneys filter it out. But in some individuals, it doesn't get filtered. Instead, it begins to collect in the synovial joints. So the synovial joints are all of your movable joints. So you can think like your fingers, your wrists, elbows, shoulders, knees, ankles, feet, toes, right? So anything that moves is a synovial joint. And synovial joints have fluid in them. And what it does, that fluid helps to like lubricate the joint so you can move without creating any kind of friction. Well, what happens is uric acid begins to build up in the joint. So you get some uric acid added in, doesn't cause a problem. More uric acid added in, doesn't cause a problem. But eventually, you reach a point of saturation, and beyond that, now you're going to get crystals. So the uric acid actually forms crystals in the joints. And so think of this as being like little shards of glass in the joint. So how do you think it feels if you move that joint? So you can imagine, think of like little tiny shards of glass, extremely painful. In fact, the joint will look bruised. The joint will turn kind of reddish purple because of bleeding that can occur because of the uric acid. If it's in your ankles or feet, you may not be able to walk on that foot while you have this gout. You can actually see the joint will swell. So you can see swelling, it'll turn real red, it gets kind of purpley looking, and that's all because of the uric acid that's there. And like I said, some people just do this. Some people just don't filter it out as well as they should. Increasing water intake helps to dilute those uric acid crystals. That can help in relieving. Decreasing, there's some connection between ingestion of certain kinds of meat, especially pork. Fried foods as well also increase the amount of uric acid that's generated. So then cutting back on those types of things, types of dietary things can help as well. There are medications if it gets really bad, but that's what causes gout. Second one, though, is kidney stones. So kidney stones, they can actually be crystals of uric acid. They can also be crystals of calcium salts. They can even be crystals of magnesium salts. So uric acid, calcium salts like calcium phosphate or calcium oxalate, magnesium salts like magnesium phosphate, all can end up becoming in such a high concentration, they become saturated. And when you go past saturation, you start to form crystals. And once you get one little crystal, then other crystals begin to form around it. So they almost grow in there, in that area. So if it's in the kidney itself, so your kidney, big job of the kidney, filtering out this fluid waste, excess salts. The kidney, once it does this filtration, it has to funnel urine towards the ureter. And the ureter is a tube that's less than 1 millimeter in diameter. Really, really small. So from the kidney, I think of the kidney as being almost like a funnel. Like at the opening of the kidney looks like a funnel. So all this urine has to funnel down into this little millimeter-sized tube. So what do you think happens if you start to build this crystal and it starts funneling down? What's going to happen when it gets here? It's going to get stuck. Okay, so it's going to end up getting stuck where it comes and narrows down. If it gets stuck in the kidney itself, worst case scenario, it can actually block urine flow, cause urine backup, and that can actually damage the kidney. So people that have kidney stones, they have to determine where it is and if it's actually affecting kidney function. If it gets into the ureter, so think of little shards of glass in a little 1 millimeter tube, and that 1 millimeter tube uses smooth muscle to try and push it along. So you can imagine the pain that comes along when people say that they're trying to pass a kidney stone. It is legit, like probably as close to childbirth as a man can get. Okay, like that kind of pain. It is an extreme pain. Again, increasing water intake, trying to kind of flush it, trying to decrease the saturation level of these salts, of these waste molecules can help. Diet can sometimes help. There's also, again, other medications that can help to limit the saturation and limit the amount of whatever stone type you have. So usually if you pass a stone or if they collect the stone, sometimes they use like vibrations to try and break the stone up. But if they can collect those stones, they send them off to figure out what kind of salt or if it's uric acid, because that way they know what you need to avoid to try and decrease the amount of stone formation. But those are examples of where saturation causes this problem. So this part we're going to talk about, we will come back and talk about this, about the strong, weak, and non-electrolytes. But what I want to spend time on today is talking about some of the math aspects. So I have like 2 more calculators. If you didn't get a calculator when you came in, you really need one. If you didn't grab a periodic table when you came in, you really need to come up and get one. So concentration, when talking about concentration, the concentration of something is just how much solute is dissolved in a certain amount of your solvent as a solution. Okay, so just think of concentration, and there's a number of different types of concentration. We're going to talk about molarity. We're going to talk about percent solutions. Maybe we'll get to parts per million, parts per billion today. I really would like to talk about them because I would like to do kind of another review on Thursday so that you have a couple of examples. You've had a little bit of time in between to kind of work on stuff. But just remember, thinking concentration, amount of the solute. Remember, the solute is the dissolved particles found in lower concentration divided by the amount of the solution. And now the solution is going to be both solvent and solutes. So when we talk about the amount of the solution, we're not just talking about the amount of water. We're talking about the amount of salt in water. We're talking the amount of glucose in water. Okay, so it's the entire content of the liquid that's making that mixture. So the first one is called molarity. So molarity really ends up having kind of 2 steps in it. So molarity is a very common concentration that's used in chemistry because it takes into account the number of molecules. So remember how you figured out moles? We talked about that way back in chapter 3. So molarity is defined as the number of moles of solute per liter of solution. Okay, so that's the difference between them. Number of moles per liter. The unit that they use is just a capital M. So if you see 2.5 capital M HCl, that means 2.5 molar HCl. So they use the term molar as a way of describing this concentration. My suggestion to you, if you see the capital M, just change out the capital M to moles per liter. Anytime you see that capital M, whatever the number is, change it to whatever that number is, moles divided by 1 liter. So 2.5 molar would be 2.5 moles divided by 1 liter. Because if I change it into this, now I have it in a measurable amount. So now it's got a unit so I can figure out how many moles I've got in a volume, and then I can convert that to grams. So if you see that capital M, it's kind of like percent. Percent is not a unit. Percent is sort of a value. So you've got to change percent back into what it stands for. So everybody got that? Because that's like one of the big things that you've got to be able to do or recognize. If you see a capital M, it means molar. Change the capital M to moles divided by 1 liter. Concentration times volume is going to tell you the amount of your solute. Concentration times volume will always equal the amount of your solute. You do have to make sure that the units will cancel, because concentration is going to be some amount of your solute over some amount of your solution. The volume has to have the same unit that your solution volume has, and that way they're going to cancel. So for example, in lab, we made soap. So we made soap by mixing, that should say by mixing a fat or an oil with 40 milliliters of 6 molar NaOH. So you remember that bottle that was in the fume hood, it was a 6 molar, and maybe you didn't notice that it had that 6 capital M in front of it, but it's a 6 molar solution. So that means what? 6M NaOH means what? What does that unit mean? What's the big M mean? 6 moles divided by divided by 1 liter. Okay, so just change that capital M into what its unit value actually means. So I'm going to multiply it times the volume. What's the volume of sodium hydroxide that I used? 40 milliliters. Well, if I just put 40 milliliters, do you see the issue with the units? Do you see that I have liters on the bottom in my concentration? So I have to convert milliliters to liters. It's just a single unit conversion. So 40 ml is how many liters? So remember to do this, 40 ml times in a line. What unit goes on the bottom? Milliliters. The unit you're starting with goes on the bottom. What unit goes on top? Liters. Whenever you see milli, what goes in front of it? 1,000. Liters always gets the 1. Well, in this. So 40 divided by 1,000 is 0.04 liters. Okay, it's just a single unit conversion because I have liters as a base unit. So now I can use this because now liters and liters can cancel. So concentration times volume is going to tell me how much of my solute. Oop, not that part. So liters and liters will cancel. So take 6 times 0.04 is equal to 0.24. So that is the number of moles. So here's A. So the first question you may be asked is, well, how many moles is that? You take the concentration times the volume. Just make sure that your volumes are in the same unit so that they'll cancel. So step 2, when you have molarity, you may have to take and convert moles to grams, but we've already done that. So what do I need to know to go from moles to grams? If I have moles to grams or grams to moles, what do I need to know? So you have to know the formula mass. So you have to add up the mass of each of the atoms in the formula. So you need the periodic table. So the formula mass for NaOH, how much does the sodium weigh? 23. How much does an oxygen weigh? 16. How much does a hydrogen weigh? 1. And I'm just going to add them up. So 23 plus 16 plus 1. Everybody see that on the periodic table? So I don't randomly just come up with those numbers. They're on the periodic table. Remember the atomic mass. So look at the periodic table. It is the larger number with the decimal place. Just round it to the nearest whole number. 23 plus 16 plus 1 is 40. So I know that there's 40 grams is equal to 1 mole. So if I know the number of moles, 0.24 moles, I can convert to grams. What do I put on the bottom in this? If I want to go to grams, what unit goes on the bottom? Moles. Grams goes on the top. In front of grams, I'm going to put the 40. Moles is going to get the 1. So 0.24 times 40. 9.6 grams. Okay, so that's how many grams of sodium hydroxide was in that solution that I added. If you have molarity, you've really got two things you have to do. You first have to do concentration times volume. Then you have to convert from moles to grams, and you need to use the formula mass to do that. So this one's kind of an opposite. So this one's like, okay, I have 88 grams of sodium chloride, and I'm adding water to make a final volume of 0.75 liters. What is the molar concentration? If I want to know the molar concentration, I want to know the big M, right? And so I know that that is moles per 1 liter. So I know grams. How do I find moles? I'm going to have to convert grams of NaCl to moles of NaCl. And once I get my moles, then I can just divide it by the volume that I have. And that'll tell me moles per liter. So figure out the first step. What do I need to find to go from grams to moles? So I need to know the formula mass. So we said Na weighs 23. Chlorine weighs 35. Does everybody see where that is? Look on the periodic table. It is the number, the bigger number with the decimal place, round to the nearest whole number. So 22.99 rounds up to 23. 35.45 just rounds down to 35. So when I add those, that is 58. So there's my unit conversion. There's 58 grams in 1 mole. What unit do I put on the bottom in the first part? Grams. Moles goes on top. Grams gets the 58. Moles always gets the 1. So notice that grams and grams will cancel. This is going to tell you the number of moles of NaCl. And when I did this, you end up with a whole bunch of numbers, yes? So I got 1.51724137.9 moles. But since this is not my final answer, I don't want to round this because this, it didn't ask for how many moles it is. What I want to know is the molar concentration. So I really want to keep all of those. I don't want to round it. Don't clear it. Instead, the second thing I have to do is I got to take those number of moles and divide by what? The volume of my solution. What's the volume of my solution? So I just want to take this number and divide by 0.75 liters. That's going to give me my answer in moles per liter. That's the molar concentration. So just keep that number and then divide by 0.75. 2.022988506 molar NaCl, right? So moles per liter, capital M, same thing. Can I keep all of those now? Because that's my final answer. 88 has how many significant figures? 2. So 88 has 2 significant figures. 0.75 has 2 significant figures. So when I come down here, 2.0, 2 significant figures. The next number is a 2. So all of that rounds down. So it rounds off. So I would just say this is 2.0 M NaCl. That is the concentration of this solution. So if you start off with a mass and you need to know molar, you have to convert from the grams to moles and then just divide it by the volume of your solution. Make sure it's in liters. All right, so here's another one to practice. So how many grams of glucose is in a 3-liter solution with a concentration of 0.65 molar glucose? And I'll even tell you the formula mass of glucose, so you don't have to figure it out. The formula mass of glucose is 180. Give you a minute, see if you can set it up. Okay, so in this, figure out what you need to find. So I want to know how many grams of glucose. So that's what I'm trying to find. I know the volume because the volume is 3.0 liters. I know the concentration is 0.65 molar. So change that 0.65 molar to what it actually means, which is 0.65 moles divided by 1 liter, right? So that's just doing this conversion to what that capital M actually means. Concentration times volume tells you how much of your solute. So 0.65 moles per 1 liter times 3 liters tells me I have 1.95 moles of glucose. Now that I have 1.95 moles of glucose, don't do any rounding, right? You don't want to end up rounding to the very end. The second step then is just convert moles to grams. And the formula mass is already given to you. So I would just take 1.95 moles of glucose times. Moles goes on the bottom, grams goes on the top. 180 with grams, moles gets the 1. That would equal 351 grams of glucose. Can I keep that whole number? Yes? No? What? What do I have to round it to? Two significant figures in 3.0. Two significant figures in 0.65. So that means that my answer can only have two significant figures, so the 3 and the 5. So that 1, this goes from 351 to, 350 grams. Sorry. Okay, so significant figures is sort of like the last thing with all of these to make sure that you double check. Just go back to the numbers in the problem, okay? And don't round till you get to the very end if this is kind of like a two-step problem. Okay, so in this one, I know the concentration, I know the volume, I figure out the number of moles. From there, I can convert to the number of grams. So it's sort of this two-step to do this. So how many grams of sodium chloride is in a 2.5 molar solution if the volume is 750 mils? How many grams of sodium chloride is in a 2.5 molar solution if the volume is 750 mils? So set this one up. And there's your reminder. Molar is always going to be whatever the number is, moles divided by 1 liter. Follow the same steps like you did just in the previous problem. Follow the exact same steps. So this one, like the last one, has 2 steps to it. First step is to figure out the amount of the solute, right? So you're going to take the concentration times the volume. So you're trying to find grams of sodium chloride, just like you're trying to find grams in the previous one. Ooh, not that way. What in the world? It's decided it's going to act wonky today. It jumped like 10 slides. Come on. Come back, come back. All right. So in this one, just like the previous one, right? The goal is to find grams of glucose. You know the volume, you know the concentration. So it's exactly the same here. I want to find grams of sodium chloride. I know the volume, I know the concentration. But my volume is 750 mils. So I have to convert that to liters because my concentration is moles per liter. So my volume has to be in liters as well. So that was really the very first step to do, is take 750 milliliters, convert it to liters. It's just a one step. So 750 times in a line, 1,000 milliliters on the bottom, 1 liter on the top. So it's 0.75 liters. Now I can take that number times my concentration, 2.5 moles per 1 liter times 0.75 liters, and I got 1.875 moles of sodium chloride. So now I know how much solute. So I know it's 1.875 moles, but if I want to know the answer I want is in grams, I've got to do one more step. So it's a second step. I need to figure out how many moles, 1.875, convert that to grams, and to do that, I have to use the formula mass. So remember, you just add up the mass of the sodium plus the mass of the chlorine. That's 58 grams is equal to 1 mole. So it's just a single step. 1.875 moles times, put moles on the bottom, grams on the top. 1.875 times 58 gave me 108.75 grams as my final answer. That's 5 significant figures. The number up at the top, how many significant figures should my answer have? Just 2. Do you see that I have 2.5? So that's 2 significant figures. 750, that's 2 significant figures. So the 1 and the 0 are the first 2 significant figures. So I would end up rounding this to what? The next number is an 8, so it would become 110. So that 8 would cause my 0 to become a 1. It would go from 108 to 110. 2 significant figures in my answer. So that's how much sodium chloride. Okay, now percent solutions are a little more straightforward. Percent solutions, you don't have to deal with moles and grams. You're just dealing with grams in a solution. So this one's really only like, you don't have to do that moles to grams calculation. The big thing is you've got to remember what percent means. So just like you get an 80% on your exam, so an 80% has no, or an 80 has no value unless you know that means it's out of 100. Well, you've had enough exams that you know that. That means that you got, on a scale of 0 to 100, you got an 80. So it gives you sort of a relevant amount. Same thing with percent. Percent puts everything on a scale of 0 to 100. So if I have a 5% sodium chloride solution, which I have written down here, 5% sodium chloride is saying 5 grams of sodium chloride per 100 mils of solution, right? So it's how much of your solute per the amount of your solution. For us, we're talking about liquid solutions, not solids, because this first one is like mass to mass ratio. So that's where everything is a solid mixed together. But for us, most of the time, it's going to be what they call mass to volume. So in that is where this comes into play. Next one, over on the other side, see where it has 12.5% of sodium chloride. That would mean that I would have 12.5 grams of sodium chloride for every 100 mils of solution. So I could make up 100 mils, I could make up 200 mils, I could make up 20 mils, I could make up any amount, but the percent is always out of 100. So like with molar, where you had to convert it to moles per 1 liter, when you see percent, take that and put whatever that number is over grams per 100 mils. Okay, just convert percent back to what it actually means. 5% means 5 grams per 100 mils. 12% means 12.12 grams divided by 100 mils. So here's one. So in this, it's again concentration times volume. So it says you want to make a 23.0% glucose solution to feed your newborn snakes. If the final volume of the glucose solution needs to be exactly 200 milliliters, because it's 200 with a decimal place, how much glucose will you need? So for this, just like with molarity, it is going to be concentration times volume will tell you the amount of your solute. Concentration times volume equals amount of solute. So what's my concentration? 23.0. What does the percent mean? What do you put after 23.0? Grams divided by 100 milliliters. That's what percent means. So take percent and convert it to grams per 100 milliliters. And now I need to multiply it times the volume. So what's the volume? So my volume is 200 milliliters. Concentration times volume. Do you see that milliliters and milliliters cancel when you do the math? 23.0 times 200 divided by 100, right? Multiply everything across the top, divide by each thing in the bottom. What do you end up with? 46. That's it, okay? So without the mole part, it's just the same. It's just really like doing the first part of the ones we were practicing. Concentration times volume is going to tell you amount of your solute. Last thing, significant figures. So 23.0, how many significant figures? 3. 200 with the decimal place, how many significant figures? 3. So 46, how many significant figures do I have in that? 2. So what do I have to add? 46.0. Okay, so it's that exact. I made 46.0 grams, 3 significant figures in my answer. Okay, do the next one. You want to make a 12% sodium chloride solution to add to your fish tank. You need a total volume of 625 mils. How much sodium chloride will you weigh out? Follow the exact same steps that we did above. Write it out. Make sure you convert percent to what it actually means, because that way you'll make sure that you have your units correct. So what's my concentration? 12 what? Grams per 100 milliliters, right? So that's what percent means. I got to multiply it times the volume, which is 625 milliliters. That way milliliters and milliliters will cancel. So you end up with 75 grams. Is that right? Can I use that or do I need to change? What's my significant figures? 12% is 2. 625 is 3, but I should always round to the lowest number of significant figures. So do I have to do anything to this? No, so I'm good. Okay? Now here's the kicker. This always like kind of throws people. So I want you to think back, have you ever made Kool-Aid? Have you ever made lemonade with a powdery drink mix? Like I can think like most people have at least done that once in their life, okay? And so when you read the package, it says, put this many scoops of lemonade and then fill two quarts. Like each of the little things makes like each of the little packages, like or scoops or whatever. So you put X number of scoops and then you add, so you make like a half a gallon at a time. 2 quarts is about a half a gallon. So do you know exactly how much water you added? No. You just know that you added enough water to make the total volume 2 quarts. That's the lemonade mix and water together, right? That's the solution, is the mix of the two of them. So this question says, how much water will you add? So think back to what you did in lab last week. In lab last week, we had to make salt solutions. So one of the salt solutions took a bit to dissolve. It was the 15%. So they had to make 15% in 100 mils. So they had to go weigh out 15 grams, put it in a graduated cylinder. So the graduated cylinder is this long tube with marks. Remember that you had to put your salt in there first, then add water. So I did have one person fill it up to 100 and said, okay, I got 100. And I said, well wait, have you added the salt yet? And they said, no. And I'm like, well, what's going to happen when you add the salt? The volume is going to go over 100, and then it wouldn't be the right concentration. So the same thing here. You don't know how much water. You only know that you add enough water to make the total volume 625 milliliters. You have to be able to put this in a container so you can measure the total volume of 625 milliliters, including the sodium chloride and the water together. Does that make sense to everybody? So you don't subtract the mass of the salt from the volume of the water, because mass and volume are not equivalent. So you can't say, oh, it would be exactly this amount. You really don't know, because as that salt dissolves, it's going to spread out, be carried within the water. Remember how sodium and the chloride ions can dissolve. You add enough water to that sodium chloride to make the total volume 625 milliliters. That is the final volume. So you really don't know the exact amount of water. Because a solution is water and solute together. Okay, so here's one more. Physiological saline is 0.90% sodium chloride. So this is the concentration of salt in your blood. Okay, it's the concentration of sodium chloride. That's why they call it physiological saline, because this would be an equal concentration of salt in the blood. So how would you make up 500 mils of this solution? Okay, so this is just another one. Concentration times volume tells you how much solute. So that's kind of like when thinking about solutions and making up solutions, that's always going to be kind of like the key part there. Concentration times volume tells you how much solute. So I've got to take my percent, change it to what it means. 0.90% means 0.90 grams of sodium chloride per 100 mils. And you can put the sodium chloride there. You could leave it off. It's still not going to change. Like I just put it in because it identifies what that solute is. That's the concentration times the volume, which is 500 mils. And I ended up with 4.5 grams of NaCl. So I just took 0.9 times 500 divided by 100 and got 4.5 grams of NaCl. So then this question, what about significant figures? How many significant figures in 0.90? 2. How many significant figures in 500? 1. So what should 4.5 be rounded to? 5 grams. Right? Because 500 only has one significant figure. If I had like a decimal place at the end, then it would be 3 significant figures, but I don't. So it's really just one significant figure. So I would end up rounding to 5 grams. Does that make sense to everyone? How would I make up 500 mils of this solution? Well, I'd take that 5 grams of sodium chloride. I'd put it in a container. It would have to have some kind of, be like a Pyrex measuring dish, glass or something like that, some way of measuring. I'd put it in a container and add enough water to make the total volume of the salt and the water equal to 500 mils. Stir it up, completely dissolves. That's physiological saline. Okay, it's a couple of practices. We'll do some more, and we'll talk, oh, here it's this, the third one. I don't think we got just enough time to cover it. Third way of looking at concentrations. What about when you have really, really, really small amounts, okay, of solutes? So when you're talking about 10%, that's 10 grams per 100 mils. That's kind of a lot of solute. But what about this? What about when you have like 5 drops of food coloring in a bathtub of water? Okay, that's not very much. It might turn that bathtub super, super blue, but it's very little solute relative to the solution. So when you get into this, now we're talking about parts per million and parts per billion. Parts per billion, they say, is like 1 drop of food coloring in an Olympic-sized swimming pool. Like that's a part per billion. That's how small that amount is. So when doing this, because it's such a small amount, if I had to put this in percent solution, it'd be like 0.0000049%. It'd be a really small percent. So that is why they went to this. Ways to solve this, what you always want to do is you want to put your answer, put your units, sorry, not your answer. Put your units in grams of solute divided by milliliters of the solution. Okay? To be able to use parts per million, parts per billion easily, put it in grams per mils. So you might have to convert for grams. If you get a number in milligrams, you might have to convert it to grams. If you get an answer of liters, you might have to convert it to milliliters. But do that first. Then multiply your answer times 1,000,000 if it's parts per million. So go to grams per mil times 1,000,000. That's a parts per million. Or multiply it times 1,000,000,000 if it's a parts per billion value. But always go to grams per mil. That way you never get it wrong, like trying to change and look at like comparisons of them. So for example, in this one, I want to know the parts per million, and I don't even tell you what the solute is, but I have 12 milligrams of solute in 250 milliliters of solution. So this is my solute. Can I keep it in milligrams? No, I want to convert it to grams, okay? So in this, 12 milligrams times in a line, what goes on the bottom? Milligrams. Your unit you're given goes on the bottom. The unit I want is going to be grams. Milli gets what? Nope. Milli is 1,000, right? Think of 1,000 years. The milli is 1,000. So there's 1,000 milligrams in 1 gram. So that means 12 milligrams is equal to 12 divided by 1,000. 0.012 grams. That's my solute. So I've got grams of solute. Do I have milliliters of solution? Yes. So I can use that directly as it is. I don't have to do any conversion. So 250 milliliters. Do you see that my units are grams per milliliter? So if I want to know parts per million, I just put it in grams per milliliters. And now I'm going to multiply it times what? Whatever this is, times a million, which is a 1 with 6 zeros. So just put it in your calculator straight as is. 0.012 divided by 250 times 1, 2, 3, 4, 5, 6. Make sure you count your zeros, because that is what I am notorious for, like leading a zero off or putting in 7 zeros. So I like literally count as I hit my zeros to make sure I get the right number. What did you get? I heard it. 48. So 48, and they call this ppm, parts per million. Try the next one. So the next one is 0.89 milligrams in 12.5 liters. So this one you had to do 2 conversions. I had to convert milligrams to grams. I had to convert liters to milliliters because I needed my units in grams per mil. So the first one I did was 0.89 milligrams times 1 gram divided by 1,000 milligrams. So I got 0.00089 grams. If anybody got anything different, let me know. 12.5 liters I had to convert to milliliters. So I had to multiply it times 1,000. 12.5 times 1,000 is 12,500 milliliters. Now I've got grams and milliliters. I just divide them. So that's 0.00089 grams divided by 12,500 milliliters times a billion. So a billion is a 1 with 9 zeros after it. So just make sure you count 1, 2, 3, 4, 5. Count the 9 out as you go through. When you multiply it times a billion, what did you get? Say it again. Yep, 71.2. So I got 71.2, and that would be ppb. Now with these significant figures, it would come into play like that one. I would end up having to round to just 71. But most of the time, parts per million and parts per billion are looking at very, very small concentrations of solutes that are oftentimes toxic. Okay, so for example, and we'll work on these ones next week, like copper in drinking water is toxic if it's above 1.3 parts per million. Arsenic is toxic in levels above 10 parts per billion. So usually rounding is not as much of the issue as much as what your answer is, and I want to compare it to what a acceptable value is. Okay, so we will practice that one a little bit more, and I have a demo to show you on Thursday.